Tonight, we're going to talk about Saturn, a planet that has been observed, measured, and studied more than almost any other object in the solar system, and it is still producing results that science cannot fully account for. Not because we haven't looked hard enough, but because every time we look, Saturn returns something we didn't expect. The physics of its interior, the behavior of its atmosphere, the structure of its magnetic field, the age and fate of its rings, every one of these threads runs deeper than the models predicted. And James Webb recently added a new layer to all of it, looking at Saturn with a sensitivity no prior observatory could match. And what it found didn't resolve the picture. It made it stranger. By the end of tonight, you're going to see exactly why scientists keep coming back to this planet and why every answer it gives raises more questions than it resolves. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Saturn is the sixth planet from the Sun, sitting about 886 million miles out at its average orbital distance. It is a gas giant, the second largest in our solar system, with an equatorial diameter of roughly 74,000 miles. 11 Earths could fit across it side by side. Its mass is about 95 times Earth's. But because it's composed mostly of hydrogen and helium gas rather than rock and metal, its overall density is actually lower than that of liquid water. If you could find a body of water large enough, Saturn would float. That fact gets cited often, and it's true, and it is about the most misleading thing you could say about Saturn, because it implies the planet is somehow insubstantial or lightweight. It isn't. Saturn's gravitational pull at its cloud tops is roughly comparable to Earth's surface gravity, about 7% stronger. The pressure at its core is estimated to be around 10 million times Earth's atmospheric pressure. The temperature near its center is believed to reach roughly 21,000 degrees Fahrenheit. The low average density is a consequence of what the planet is made of, not an indication of its gentleness. Beneath the visible cloud layers is a layered structure of increasing pressure and temperature that has been defying our models in important ways since we began studying it carefully. We've known about Saturn since antiquity. Ancient Babylonian astronomers tracked it across the sky and recorded its position systematically. Ancient Greeks named it after Kronos, the Titan who ruled time. The Romans called it Saturn, their deity of agriculture, wealth, and generation. The name stuck. Galileo looked at Saturn through one of the first telescopes in 1610 and was genuinely confused by what he saw. He perceived three objects: the main planetary disk flanked by two smaller companions. He didn't understand the geometry. He wrote to a colleague in coded form, an anagram in Latin, to claim observational credit without committing to an explanation he wasn't confident in. It wasn't until 1659 that Christian Huygens, using a better telescope and a more patient mathematical analysis, worked out the truth. The flanking objects were a flat ring of material orbiting Saturn in its equatorial plane. Nothing else in the known cosmos had been seen to have anything like them. For the next 3 centuries, the rings were the entire story. Saturn was the ringed planet. That label defined everything about how scientists and the public thought about it. Then came the spacecraft. Pioneer 11 made the first close flyby in 1979, returning grainy but genuine close-range images of the planet and its ring structure. Voyager 1 followed in 1980. Voyager 2 arrived in 1981. The Voyager flybys returned the first high-quality images of Saturn's moon system. The ring gaps, the atmospheric banding, they also returned something else. Data that didn't quite fit the model. Not dramatic anomalies, not phenomena that leaped off the screen, subtle patterns. Things that got noted in publications and then sat quietly in the literature, while researchers tried to determine if they were instrumental in origin or genuinely telling us something new about Saturn. Every single one of them turned out to be real. Every anomaly that emerged from Voyager was confirmed, deepened, and complicated by Cassini. And then Webb came along and complicated them further. The strangeness starts with something invisible to ordinary observation: radio waves. Saturn emits radio waves, as most of the large planets do. Jupiter's radio emissions are so powerful they can be picked up by amateur radio equipment on Earth when the geometry is right. Saturn's emissions are subtler, but they pulse. They carry a periodic rhythm, and for decades, that rhythm was assumed to be one of the most fundamental things you could know about a planet: its rotation rate. The reasoning was entirely sound, because it had worked before. Jupiter's radio emissions are tied to the rotation of its magnetic field, which is in turn coupled to the deep interior through the electrically conducting metallic hydrogen zone. Measuring the period of Jupiter's radio pulses gives you the rotation period of its interior. The same logic, the same physics, should apply to Saturn. Saturn's characteristic radio signal was named Saturn Anomalous Myriametric Radiation. The name comes from the wavelength range, myriameter scale wavelengths, the longest radio waves, which propagate efficiently through the interplanetary medium. Voyager measured its pulse period at approximately 10 hours and 39 minutes. That number entered the planetary science literature as Saturn's rotation period. It appeared in textbooks. It was published in data tables alongside the planet's other physical characteristics. It was used as the baseline reference for calculating atmospheric wind speeds, because if you know the rotation rate of the interior, you can subtract it from the observed cloud motions to get how fast the atmosphere is actually moving relative to the deep planet. It seemed settled. It was the kind of number you cite and move on from. Then Cassini arrived and listened carefully for 13 years. And what it found undid everything. The period wasn't constant. It varied by several minutes over the course of months. Not randomly, not in ways consistent with instrumental noise. Systematically. And it varied differently depending on which hemisphere you were listening from. The northern hemisphere emitted radio pulses with a period of approximately 10 hours and 36 minutes. The southern hemisphere emitted with a period of approximately 10 hours and 48 minutes, 12 minutes apart, north and south, on the same planet, pulsing at different rates. A planet's deep interior spins as a single rigid or near-rigid body. It has one rotation rate. 1. If the radio signal were genuinely tracing the interior rotation, the north and south hemispheres would agree, because the interior is the same for both. They don't agree. So the signal is not coming from the deep interior in the simple way that everyone assumed for decades. Something closer to the surface, something that can be different in the north than in the south, is generating or modulating these radio pulses in a more complicated fashion. And then, buried inside the dominant pulsing signal, 18 years of Cassini data eventually revealed a second periodicity, a nested rhythm within the first. Two overlapping signals, both pulsing, one inside the other. It had been there from the beginning, hidden in data that had been collected, processed, and published. No one had extracted it. It required the full duration of Cassini's mission, the full archive of its measurements, and sophisticated analysis techniques to find. The leading explanation today involves Saturn's rings acting as an intermediary between the atmospheric dynamics and the radio emissions. Density waves and bending waves propagate through the ring structure, driven by gravitational resonances between the rings and Saturn's many moons. These ring waves can excite oscillations in Saturn's upper atmosphere at specific latitudes. If those atmospheric oscillations are organized enough, they can interact with the magnetic field near the poles and imprint their periodicity on the structure of the radio emissions. The northern atmospheric wave system has one period. The southern has a slightly different one. 2 atmospheric periodicities, 2 radio signals. But this explanation immediately generates the next question, which is what drives and maintains the atmospheric wave patterns that are supposedly producing the radio signals. And the answer to that leads directly into the interior, into the helium rain, into the internal heat, into the physical state of the material thousands of miles below the clouds. The radio anomaly is not a surface phenomenon wearing a surface explanation. It is a surface expression of interior physics that we are still working to fully characterize. What is certain, what is simply undeniable, after all the observations, is this: we do not know Saturn's interior rotation rate. After Voyager, after 13 years of Cassini, after decades of ground-based observations, after Webb, after the application of ring seismology techniques that treat propagating waves in Saturn's rings as oscillation modes capable of probing the interior, the current best estimate is around 10 hours and 33 minutes, give or take roughly a minute. Better than the original Voyager measurement. Not definitive. This is not a small admission. The rotation period of a planet is foundational to planetary science. Internal structure models are built on it. Atmospheric dynamics calculations depend on it. Comparisons between Saturn and Jupiter, between Saturn and other gas giants in exoplanet surveys, use it as a reference point. If the rotation rate is wrong or uncertain, everything built on it accumulates that uncertainty. We have been uncertain about the rotation rate of the 6th planet from our Sun for decades. We still are. That's the first anomaly. Saturn's North Pole is where things get strange. Something is there that atmospheric science says should be far less stable than it is. Voyager 2 detected it in 1981, a hexagonal pattern in the cloud structure at Saturn's North Pole, approximately 20,000 miles across. Each of its 6 sides, roughly 9,000 miles in length, wider than Earth's diameter. The scientists who received the data reacted with skepticism. Atmospheric fluids don't form sharp hexagons. They form ovals, circles, vortices, meandering jet streams, and chaotic turbulent bands. Not geometric polygons with 6 straight sides and 6 sharp corners. The data was reprocessed. Alternative explanations were considered. The hexagon was still there. It was real, and it has been there, confirmed in every observation made since, for over 45 years. The same shape. The same, approximately 20,000 mile scale. The same 6-sided geometry. Essentially unchanged across 4.5 decades of direct measurement. Atmospheric physics does have mechanisms that can produce polygon-like structures in rotating fluids. Laboratory experiments, conducted as far back as the 1980s, have reproduced hexagonal wave patterns by rotating a tank of fluid at specific rates with a spinning inner cylinder. The mechanism involves a fluid instability called a barotropic instability, which arises when a gradient in rotation rate exists between different regions of a fluid. Under the right conditions, unstable wave modes emerge and lock into a geometric shape. The number of sides depends on the rotation rates and the geometry of the system. Hexagons are achievable. The physics is reproducible in a laboratory tank. But a laboratory hexagon, maintained by precisely controlled and constant experimental conditions in a tank you can turn off and restart, is an entirely different object from a hexagonal wave structure in a real planetary atmosphere. Saturn's atmosphere is not a controlled experiment. It is subject to continuous gravitational perturbations from dozens of moons pulling on the atmosphere from different angles as they orbit. It receives variable solar heating as the planet orbits the Sun and as the seasons progress. It is driven from below by internal heat from the helium rain process, a heat flux that changes on geological timescales. The atmosphere interacts with Saturn's magnetic field. It receives impacts from small meteorites. It responds to auroral heating near the poles. With all of that ongoing, the hexagon holds. Not approximately. Not with measurable drift or degradation. Precisely and geometrically, decade after decade, in a real planetary atmosphere at a scale 2.5 times wider than Earth's diameter. The most direct test of what maintains the hexagon came from Saturn's polar seasons. Saturn's axial tilt of about 27 degrees means the poles experience dramatic seasonal changes in sunlight. During Saturn's northern winter, the North Pole is tilted away from the Sun and receives no direct sunlight. Polar night at planetary scale. For years. Sunlight drives most of the dynamic atmospheric structures we observe on giant planets. It creates temperature differences between latitudes that power jet streams and maintain weather patterns. It energizes photochemical reactions that affect cloud formation and composition. Without sunlight, these solar-driven processes stop. The hexagon received zero solar energy during Saturn's northern winter. Not diminished input. Zero. And it persisted without measurable change through the entire duration of polar night. When northern spring returned and sunlight began falling on the pole again, the hexagon was still there. Same geometry, same rotation period, same scale. The conclusion from this is clear and unavoidable. Solar heating is not what maintains the hexagon. The mechanism that sustains it operates on energy from inside Saturn, not from outside. The hexagon is fed from below. Inside the hexagonal boundary, at the pole itself, there is a massive cyclonic vortex, approximately 1,200 miles across. A polar hurricane with a clear central eye, organized spiral cloud bands, and high-velocity winds circling the calm center. Two structures nested inside each other. The inner polar cyclone spinning. The outer hexagonal boundary maintaining its six-sided geometry, both running continuously, both stable, both present across every observation we've made. Wind speeds at the hexagonal boundary reach approximately 200 miles per hour. The polar cyclone shows organized, structured winds around a central eye region, a pattern resembling the extreme tropical cyclones on Earth, but stationary at the pole, not drifting across an ocean surface. When Cassini tracked the hexagon systematically over its 13-year mission, it documented a dramatic color change across Saturn's seasons. When Cassini arrived in 2004, Saturn's North Pole was deep in winter. The polar atmosphere was cold and dark, and the hexagon appeared in a striking blue color, a consequence of the specific particle sizes and chemistry in the cold polar atmosphere, scattering light differently than the surrounding atmosphere. As the mission continued and Saturn moved in its orbit, northern spring began. The color shifted. Blue-gray first, then deeper blue, then gradually the yellows and tawny oranges of late spring and early summer. Photochemical reactions, initiated by returning sunlight, generated aerosols, organic haze particles, that changed the optical properties of the polar atmosphere. A dramatic color transformation. The color changed from winter blue to summer gold over the course of the mission. The shape did not change. The hexagon and the polar cyclone survived the entire transition from polar night to spring to summer with their geometry intact. Whatever process maintains, the hexagon is running on timescales much longer than Saturn's seasons. It is older than the current season. It may be much older. We know it has been there for every moment since we first had instruments capable of detecting it. Whether it has existed for centuries or since Saturn formed, we cannot determine from 45 years of observation against a geological timescale of 4.5 billion years. On November 29, 2024, James Webb turned to Saturn. Specifically, its mid-infrared instrument, MIRI, which operates at wavelengths that Earth's atmosphere absorbs completely, making them inaccessible to any ground-based telescope. MIRI doesn't see reflected sunlight. It sees thermal emission, heat coming directly from the planet and its atmosphere. When MIRI turned to Saturn's North Pole, the hexagon resolved into something considerably more architecturally complex than visible light imagery had revealed. In the infrared, the hexagonal structure appeared not merely as a cloud-level boundary between different air masses at a single altitude, but as an organized thermal feature with coherent structure across multiple atmospheric levels simultaneously. Temperature differences associated with the hexagonal geometry could be traced from one altitude level to another in a continuous, organized pattern. The hexagon is not a single altitude surface phenomenon. It has vertical extent. It is three-dimensional in a way that simple surface wind patterns cannot produce. Driving a coherent structure through multiple altitude levels requires that the dynamical process sustaining it is communicating across those levels, coupling the upper and lower atmosphere in a way that maintains the geometric pattern from one layer to the next. This is a deeper, more interconnected process than previous data had clearly established. The hexagon reaches into the atmospheric column. It is not a shallow feature. It is not a surface eddy. It is an organized, dynamical structure with depth. And then, within the polar region, distributed through the hexagonal thermal structure, MIRI detected something that no prior instrument had seen. Dark, drifting features. Discrete concentrations of material moving through Saturn's polar atmosphere. Their trajectories did not match the simple background circulation that models of the polar atmosphere predicted. They drifted on their own paths within the hexagonal structure, at rates and in directions that current dynamical models had not anticipated, large enough to be spatially resolved at Saturn's distance, which means each feature is enormous, potentially thousands of miles across. Their nature is still being characterized as the data is analyzed. Current hypotheses suggest they may be related to wave-driven dynamics in the upper stratosphere, where wave energy from the hexagonal wave structure below propagates upward and interacts with the stratospheric environment to produce organized large-scale patterns. But the hypotheses are preliminary. there is no consensus interpretation yet. The scientific community is still working through what the data means. What's notable about these features is precisely that they were not predicted. Nobody built a model of Saturn's polar atmosphere and said, "Look for dark drifting structures in the infrared data." They appeared in the data unexpectedly. That is the signature of a genuine discovery. Webb also captured Saturn's aurorae in infrared with unprecedented clarity. Saturn's auroral emission is primarily infrared, produced by excited hydrogen molecules near the poles that glow when energized by incoming charged particles. Earth's atmosphere absorbs the relevant infrared wavelengths, making ground-based auroral observation at Saturn difficult. Webb doesn't have that limitation. The auroral images showed organized structure at both poles, with intensity variations and geometric patterns that, combined with the hexagonal thermal maps and the long-standing radio emission anomalies, complicated the picture of Saturn's polar magnetic environment considerably. Asymmetries between north and south, intensity variations that correlated, at least partially, with the timing of the northern and southern radio emission periods. The connection between the aurorae, the hexagon, and the radio emissions suggests they are all aspects of a common underlying magnetic and dynamical system that is more intricately coupled than previous models suggested. And all of this connects back to the most fundamental strangeness about Saturn's magnetic field. Saturn's magnetic field is nearly perfectly aligned with its rotation axis. The angular offset between the magnetic pole and the geographic pole is less than 1 degree. This is unique in the solar system. Every other planet with a significant internally generated magnetic field has a measurable tilt between the magnetic axis and the rotation axis. Earth's magnetic pole is currently about 11 degrees away from the geographic pole, and this offset drifts measurably over decades. Jupiter's field is tilted about 10 degrees. Uranus's is tilted about 60 degrees. Neptune's is tilted about 47 degrees. Saturn's is less than 1 degree. This near-perfect alignment presents a fundamental problem for dynamo theory. Planetary magnetic fields are generated by the flow of electrically conducting fluid in a planet's interior. For Saturn and Jupiter, the relevant conducting fluid is metallic hydrogen, a phase of hydrogen that forms under pressures so extreme that electrons flow freely through the material, giving it the electrical conductivity of a metal. Flowing metallic hydrogen creates electrical currents. Those currents generate magnetic fields. The magnetic field influences the flow of the metallic hydrogen, which in turn maintains and modifies the current. A self-sustaining feedback loop, the dynamo. Standard dynamo theory requires that the field have some degree of asymmetry to sustain itself in the feedback loop. A perfectly symmetric, perfectly aligned configuration does not drive the self-sustaining feedback cycle. The field decays. Saturn has a magnetic field approaching that forbidden symmetric configuration. And yet Saturn has a strong, well-organized, long-lived magnetic field. These two facts in combination violate what the theory predicts should be possible. The current leading hypothesis involves an intermediate layer of differentiated material at an intermediate depth inside Saturn. As helium has been separating from metallic hydrogen and raining inward over billions of years, a shell of material has accumulated at the interface between the metallic hydrogen zone and the outer molecular hydrogen envelope. This shell has a different composition and different physical properties from the layers above and below it. It may act as an electromagnetic filter, preferentially allowing large-scale, axially symmetric components of the magnetic field to pass through while suppressing the asymmetric, tilted components that a standard dynamo would typically generate. What we observe outside the planet is the filtered version of the field. The internal dynamo may be producing a complex, tilted field. The filter removes the asymmetry before it reaches the surface. The external field looks nearly perfectly aligned, not because the dynamo is perfectly symmetric, but because something between the dynamo and the surface is removing the asymmetry. This hypothesis is testable. It makes predictions about Saturn's internal mass distribution and about the detailed structure of the magnetic field at close range. Cassini's grand finale, Orbits in 2017, gathered the gravitational and magnetic field data needed to constrain these models. Papers based on that data continue to be published. The models are still being refined. The near-perfect magnetic alignment remains, as of today, not fully explained. It's a real anomaly. It's connected to the helium differentiation. It's connected to the radio emissions. It's connected to the heat output. Everything, again, leads back to what's happening inside. Saturn emits about 1.8 times as much energy as it receives from the Sun. At Saturn's orbital distance, the Sun's flux is about 1% of what reaches Earth. Saturn is a long way out. For the planet to radiate nearly twice the energy it absorbs, it must have an internal heat source of significant power that operates continuously. Jupiter also has excess heat output, about 1.7 times its incoming solar energy. For Jupiter, the explanation is well constrained. Jupiter is massive enough to have been slowly contracting under its own gravity since it formed 4.5 billion years ago. Kelvin-Helmholtz contraction. Gravitational potential energy converted to heat as the planet slowly shrinks. At Jupiter's mass, this process alone generates enough heat over 4.5 billion years to account for the measured excess. The math works. Saturn is smaller, significantly smaller. At Saturn's mass, Kelvin-Helmholtz contraction does not generate enough heat. The calculation comes up short. There is a gap. Something else must be generating heat inside Saturn that isn't generating comparable heat inside Jupiter. The answer is helium rain, and understanding it requires understanding the state of matter at extreme pressures. Both Saturn and Jupiter contain metallic hydrogen in their interiors. Under the immense pressures that exist deep inside a gas giant, tens of millions of times atmospheric pressure, hydrogen undergoes a phase transition. It becomes metallic. Electrons in hydrogen atoms are stripped from their nuclei and flow freely through the material, the same way electrons flow through actual metals. Metallic hydrogen conducts electricity. That's what enables the magnetic dynamo in both planets. In Jupiter's metallic hydrogen zone, the temperatures are high enough that helium remains dissolved throughout the region. Helium atoms mix freely with the metallic hydrogen in the way that dissolved salt mixes with water, without separating into its own distinct phase. In Saturn's metallic hydrogen zone, the situation is different. Saturn is smaller than Jupiter. It formed from a less massive protoplanetary core. It has had 4.5 billion years to cool. As a result, the temperatures in Saturn's metallic hydrogen zone today are lower than in Jupiter's metallic hydrogen zone. At those lower temperatures, the solubility of helium in metallic hydrogen decreases. Helium becomes less able to remain dissolved at a given concentration. At some pressure and temperature combination within Saturn's interior, helium reaches its saturation point in the surrounding metallic hydrogen. It begins to separate out. Tiny droplets of helium form, the way bubbles form when a carbonated liquid becomes supersaturated. These droplets are denser than the surrounding metallic hydrogen. Gravity pulls them inward. They sink towards Saturn's center. They fall. As they fall, converting gravitational potential energy into heat, they warm the surrounding material. Billions upon billions of droplets, continuously forming at the saturation boundary and continuously sinking inward. 4 billion years of this process. This is helium rain, and it has two direct, measurable consequences. The first is the depletion of helium in Saturn's upper atmosphere. When the solar system formed, Saturn assembled from the same primordial mixture of elements that formed the Sun and the other planets. That mixture contained roughly 71% hydrogen and 28% helium by mass, numbers that reflect the composition of the early universe with some stellar processing. Jupiter's atmospheric helium fraction is around 24% by mass, broadly consistent with the primordial solar composition. Saturn's atmospheric helium fraction is measured at roughly 11 to 13%, significantly lower. Not because Saturn formed with less helium, because 4 billion years of helium rain have stripped helium out of the upper layers and transported it toward the deep interior. The upper atmosphere is depleted. The core region is enriched. Cassini measured Saturn's atmospheric helium abundance directly using its mass spectrometer during atmospheric sampling and confirmed the depletion. This is not a model prediction checked against observations. This is a direct measurement. The helium is missing from where it should be. The second consequence is thermal. When you calculate the gravitational energy released by the continuous downward migration of helium through Saturn's interior over 4.5 billion years, the numbers close the gap. The energy produced by helium rain, added to the energy produced by Kelvin-Helmholtz contraction, equals the total measured excess heat output. The accounting works. Saturn's anomalous heat output is explained. But what the explanation reveals is that Saturn's behavior today, every surface anomaly we observe, is driven by a process that has been running since the planet formed. The helium rain generates excess heat. The excess heat drives atmospheric convection on multiple timescales. It feeds the deep dynamics that maintain the hexagonal wave pattern. It supplies the energy for the 30-year megastorm cycle. The helium rain has also changed the composition of the metallic hydrogen zone over billions of years. As helium migrated out of the metallic hydrogen zone, it left behind an intermediate layer of differentiated material that filters the magnetic field before it reaches the exterior. The nearly perfect magnetic alignment we observe is a product of 4 billion years of helium differentiation, reshaping the interior. The radio emissions, modulated by atmospheric wave structures, driven by convection, driven by excess heat, driven by helium rain, are part of the same chain. The ring rain, the rate at which ring material spirals into Saturn's atmosphere along charged magnetic field lines, depends on the geometry and strength of the magnetic field, which depends on the helium rain process. The megastorms are fed by the same interior heat. Everything connects. Saturn is one system, driven from the inside, expressing itself at the surface in ways we can measure but have not fully explained. Saturn has weather. Not weather in any sense that reduces to the phenomena we experience on Earth. Something else. Something that operates on timescales that stretch across human generations and releases energy on scales that are difficult to express without numbers that feel abstract. Every 30 Earth years, roughly once per Saturn year, a storm breaks out in Saturn's northern hemisphere. Not a tropical cyclone, not a planetary scale weather system like the kinds that occasionally disrupt a region of Earth. A storm that, within weeks, grows to encircle the entire planet in a band of white cloud. These events are called Great White Spots. The name is understated. Documented observations of them extend back to 1876, when American astronomer Asaph Hall observed a bright white feature expanding across Saturn's disk. Additional events were recorded in 1903, 1933, 1960, 1990, and 2010. 6 documented events. 6 approximately 30-year intervals. The timing is not random. The 30-year cycle tracks Saturn's orbital period around the Sun, which means the storms happen at approximately annual intervals on Saturn's own calendar. 1 storm per Saturn year, in the Northern Hemisphere near the Northern Hemisphere summer solstice. The mechanism begins with Saturn's internal heat and the way it interacts with the upper atmosphere. Between major storms, heat generated by the helium rain flows upward through Saturn's interior. This heat accumulates in the troposphere, the weather layer, particularly in the region around the water cloud level, which lies deep in the atmosphere where pressures are many times Earth's surface pressure. As heat accumulates below the water cloud level, the temperature in that region gradually rises. The water vapor in the cloud layer represents stored energy in the form of latent heat, energy that is released when water vapor condenses into liquid or ice. As the tropospheric heat reservoir deepens over years and decades, the potential energy available to any convective event that could tap it grows. But the layer above the troposphere, the lower stratosphere, is stable. Temperature and density are distributed in a configuration that strongly resists vertical mixing. The stable stratospheric layer acts as a lid. It suppresses the convective overturning that would normally allow heat to escape upward from the troposphere. The energy accumulates below the lid, year after year, decade after decade, 3 decades. The question is, what finally breaks the seal? Every documented great white spot has formed in Saturn's northern hemisphere, and the timing consistently correlates with the approach of the northern hemisphere summer solstice. Every 30 years, Saturn's northern hemisphere reaches maximum solar illumination as it faces the sun during the northern summer. The additional solar input at the summer solstice creates a small additional perturbation in the upper atmosphere, a minor additional heating that nudges the stability of the stratospheric lid. On a background that has been building for 30 years, this small perturbation is enough. The lid breaks locally. A massive convective plume erupts upward from the water cloud level. It carries enormous volumes of heat, moisture, ammonia, ice, and deep atmospheric chemistry upward into the stratosphere. The rising column is hot and buoyant. It punches through the stable layer that has been capping it for 30 years. And once the initial eruption breaks through, the process feeds itself. The rising column of warm, moist air creates a region of lower pressure at its base. Surrounding atmosphere rushes in to fill the gap. The inflow creates wind patterns. Wind shear generates electrical charge separation. Lightning occurs. Condensing moisture in the rising column releases latent heat, adding energy to the updraft. The storm grows. Not linearly. Explosively. Within days of the initial outbreak, the storm's bright white cloud head is visible from Earth-based telescopes as a small white spot on Saturn's disk. Within weeks, the head has expanded dramatically and is traveling rapidly eastward, extending a trail of disturbed white cloud material behind it as it goes. Within months, the storm band wraps completely around Saturn's circumference at its latitude, an unbroken band of white cloud encircling the entire planet. The 2010 Great White Spot was observed by Cassini, which had been in orbit around Saturn since 2004 and had its full suite of instruments operational throughout the storm. The data Cassini returned from that storm is extraordinary in its detail. The storm began in early December 2010 in Saturn's northern hemisphere. Within weeks, it had developed a convective head reaching approximately 200 miles above the surrounding cloud deck. The white material in the head was primarily ammonia ice crystals. Deep in Saturn's atmosphere, ammonia exists as gas and liquid at high temperatures. The convective plume carried ammonia-rich gases upward to altitudes where temperatures dropped far below ammonia's freezing point. The ammonia froze. Bright white crystals formed. The white scar, visible across Saturn's northern hemisphere, was freshly crystallized ammonia, carried up from depths where it had been in gaseous form for decades. Cassini's radio and plasma wave science instrument measured lightning within the storm continuously for months. Saturn's lightning is not comparable to Earth's. Typical lightning on Earth releases on the order of 1 billion joules. The individual lightning events in the 2010 storm were orders of magnitude more energetic, and they occurred continuously, not occasionally, not in periodic bursts, continuously at rates of thousands of flashes per hour for months. Researchers totaled the cumulative electrical energy output of the 2010 storm across its full, active period. They compared it to the total amount of solar energy that Earth receives over the course of 1 year. The numbers were roughly comparable. A single storm on one planet generated total lightning energy roughly equivalent to a full year of Earth's solar input. The atmospheric violence is on a scale that has no terrestrial reference point. As the storm head traveled eastward around the planet over the following months, the storm's trailing tail stretched out behind it. In late summer 2011, the storm head completed its circuit of the planet. It approached the trailing tail of the storm from the west. The head and the tail, both still maintaining active convection, collided. What happened in that collision was not a merger. The two massive convective systems annihilated each other. Both collapsed simultaneously. The enormous cloud towers that had been sustaining the storm on both ends fell apart at roughly the same time. The visible storm activity ended abruptly in a mutual destruction, but the aftermath persisted for years. Cassini continued monitoring Saturn's stratosphere after the storm's visible end. For more than 3 Earth years, chemical anomalies remained detectable at the storm's latitude. Compounds carried up from depth by the original convective plume, materials not normally present at stratospheric altitudes, were still visible in Cassini's spectrometer data, slowly diffusing, slowly being broken down by stratospheric photochemistry. The storm lasted months. its chemical signature lasted years. The next great white spot is expected in the approximately 2045 to 2050 window. The precise timing depends on how Saturn's seasonal dynamics evolve, and the 30-year interval has some variability. When the storm breaks out, we will observe it. Whether we will have spacecraft in orbit at Saturn to observe it at the kind of close range that Cassini provided is an open question that depends on funding decisions being made in the coming years. There are mission concepts under discussion. Nothing is committed. If no mission is flying at Saturn during the next great white spot, the storm will be observed from Earth-based telescopes and from Webb, and we will see the planetary scale event. We won't be inside it. We won't get the Cassini-level electromagnetic and chemical detail. The next storm may come and go and be watched entirely from a distance of 800 million miles. The science we extract from it will be limited by that distance. Look at the rings. The ring system of Saturn spans roughly 170,000 miles from the inner edge of the D ring to the outer edge of the F ring. The main visible ring structure, the A, B, and C rings, extends from about 43,000 miles above Saturn's cloud tops to about 77,000 miles. In most parts of the main ring system, the vertical thickness is less than a few hundred feet. The thinnest regions are as thin as 60 feet, 170,000 miles wide, 60 feet thick. If you scaled the main ring system to the dimensions of a sheet of paper, the sheet would be several feet across. The ratio of width to thickness makes the rings one of the geometrically most extreme flat structures known in the solar system. They are made primarily of water ice, ranging from microscopic dust grains to chunks several yards across. Rocky material and dark organic compounds are mixed in at lower concentrations. The particles orbit Saturn in a plane, aligned precisely with the planet's equator. Because Saturn's gravitational field has directed everything in its orbital zone toward equatorial alignment over geological time. The ring structure has distinct regions separated by gaps. The B ring is the brightest, most massive, and most visually prominent component. The A ring sits outward of the B ring. Between them, the Cassini division, a gap about 2,900 miles wide that appears dark in comparison to the bright surrounding rings. The Cassini division exists because orbital material at that distance from Saturn completes one orbit for every 2 orbits completed by the moon Mimas. This 2-to-1 resonance means Mimas exerts a gravitational kick on anything in the Cassini division zone twice per orbit, repeatedly in the same direction. Over millions of years, these repeated kicks amplify any small perturbation in the material's orbit until the orbit becomes eccentric enough to intersect other ring orbits, causing collisions that scatter the material. Material is cleared from the Cassini division zone by the resonance with Mimas. The gap is a gravitational sculpting mark. The C ring sits inward of the B ring, darker and less massive. Inside the C ring, the faint D ring extends inward to just above Saturn's cloud tops. Outside the A ring, the narrow F ring is maintained by 2 small shepherd moons, Prometheus and Pandora, whose competing gravitational influences constrain the ring material into a narrow, kinked strand. The ring system also includes many smaller ringlets and gaps within the main rings, most too narrow to see from Earth, but clearly resolved in Cassini's images. Each gap is associated with a gravitational resonance with one of Saturn's moons, or with a small embedded moonlet whose gravity prevents material from filling that orbital zone. The rings are not static. Material moves constantly within them. Density waves, driven by gravitational resonances with the moons, propagate outward through the ring plane like ripples on a pond. Vertical bending waves raise material above and below the ring plane in rhythmic corrugations. Clumps of material aggregate and disaggregate. The ring system is a dynamic, continuously evolving structure, and the most important thing modern planetary science has established about it is its youth. The rings are young, not ancient, not primordial features that have existed since Saturn formed 4.5 billion years ago. Young. The evidence for this comes from multiple independent lines of reasoning, and they all converge on the same answer. The total mass of the ring system was measured precisely by Cassini during its grand finale orbits, in which the spacecraft flew close enough to Saturn to isolate the gravitational influence of the rings from Saturn's own gravitational field. The result? The total mass of Saturn's main ring system is roughly equivalent to about 40% of the mass of the Moon Mimas. Surprisingly low. A ring system that has been accumulating material from infalling meteorites for 4.5 billion years would have accumulated vastly more mass than this. Old rings are heavy. Saturn's rings are relatively light. The brightness confirms the same picture. Water ice is reflective. Old ring systems get contaminated by dark, carbon-rich material falling in from the interplanetary medium, the steady rain of micrometeoritic particles that permeates the inner solar system. Saturn's main rings are bright, highly reflective, relatively uncontaminated. The contamination rate is measurable, and if you work backward from the current level of contamination to determine how long it would take to reach that level, you get a young age. A comprehensive analysis published in 2023, incorporating data from across the Cassini mission combined with ground-based measurements, concluded that Saturn's rings formed somewhere between 10 million and 100 million years ago. The solar system is 4.5 billion years old. If the rings formed at the midpoint of that range, 50 million years ago, that's in the Eocene epoch on Earth. Early primates. No modern humans. No grasslands. No ice ages yet. The rings of Saturn did not exist when complex animals first evolved on Earth. They did not exist when the first fish colonized the land. They did not exist when the dinosaurs arose and ruled the planet. They appeared in a cosmically recent moment, long after the major milestones of Earth's evolutionary history had already occurred. We are observing Saturn at the one brief interval in the solar system's history when its rings are present. There is a version of this that is difficult to sit with. If a civilization had developed on some other planet in our solar system, hundreds of millions of years earlier, or hundreds of millions of years later, Saturn would have been just another gas giant. Featureless. Unremarkable. The defining visual feature of Saturn, the feature that makes it the most recognizable planet, the feature that inspired centuries of scientific investigation, was not there for most of history and will not be there for much of the future. We arrived at exactly the right time. The rings came from something, from a moon that no longer exists. A moon destroyed by Saturn's own gravity tens of millions of years ago. Researchers at MIT published this hypothesis in 2022, and it resolved a puzzle that had been sitting in planetary science for a long time alongside the ring age question. The puzzle was Saturn's axial tilt. Saturn is tilted about 27 degrees relative to the plane of its orbit around the Sun. This tilt is the reason Saturn has seasons, the reason the hexagon experiences polar night, the reason the rings appear at different angles when viewed from Earth as Saturn moves through its orbit. Planetary formation models have a problem with that tilt. The dynamical processes that formed the solar system do not naturally produce a 27-degree tilt in a planet Saturn's size. The planet should have formed with a much smaller tilt. Something tilted it. For a long time, the leading explanation was a gravitational resonance with Neptune. As Neptune migrated outward during the solar system's early chaotic dynamical period, driven by interactions with the primordial disk of small bodies beyond it, Saturn's axial precession frequency, the rate at which Saturn's rotation axis slowly wobbles in a circle, gradually aligned with Neptune's orbital period. When a precession frequency aligns with an orbital period, the two objects can exchange angular momentum. A resonance forms. Over millions of years, that resonance can drive a planet's tilt away from zero. The calculations suggested that the resonance with Neptune could have tilted Saturn to something close to its current angle. But the numbers for the resonance only worked if Saturn had a moment of inertia, a measure of how its mass is distributed internally, that was slightly different from what current measurements indicate. Different enough that an additional large moon, one not presently in the Saturn system, would have been needed to provide the additional gravitational coupling to lock Saturn firmly into the resonance. A moon that doesn't exist anymore. The MIT team modeled the scenario. Saturn once had an additional large moon in an outer orbit, a moon roughly comparable in size to Iapetus. This moon's gravitational influence helped lock Saturn into the Neptune resonance at the right epoch, providing the coupling that tilted Saturn to its current angle. But the moon's orbit was not stable. Gravitational interactions with the other large moons, primarily Titan, perturbed the orbit over hundreds of millions of years. The orbit became increasingly elongated over time. The moon's closest approach to Saturn crept inward, slowly. Eventually, it crossed Saturn's Roche limit. The Roche limit is the distance from a planet inside which the planet's tidal forces become stronger than an object's self-gravity. Outside the Roche limit, a moon held together by its own gravity can exist stably. Inside the Roche limit, the differential gravitational pull across the object's diameter, stronger on the near side than on the far side, exceeds the force holding the object together. The object is pulled apart. The moon crossed the Roche limit. Tidal forces stretched it, cracked it, shattered it. Its icy body disintegrated into billions of fragments, which spread through the orbital plane in a disk of debris. Over millions of years, that debris field settled through collisions into the flattened, organized ring structure we see today. And the destruction also released Saturn from the Neptune resonance. When the moon was gone, the gravitational coupling that had maintained the resonance broke. Saturn's axial tilt, established during the resonance phase, was preserved as a fossil of the interaction. 27 degrees, frozen into the planet by the gravitational influence of a moon that was then destroyed. The same moon whose destruction created the rings. The tilt and the rings are consequences of the same event. One moon, one disruption, two lasting effects. A tilt frozen into the planet's geometry. A ring system slowly draining back into the planet it came from. The MIT team called this hypothetical moon chrysalis. The name fits. Something transformed. something emerged from the transformation. Something else was left behind. The rings are disappearing. Not as a future possibility. Now, measurably. Ring particles in the innermost parts of the ring system are continuously exposed to ultraviolet radiation from the Sun and to energetic charged particles in Saturn's magnetosphere. These interactions charge the particles electrically. Once a ring particle acquires an electric charge, it no longer behaves purely as an orbiting body responding to gravity. It also responds to Saturn's magnetic field. Saturn's magnetic field lines connect the ring plane to Saturn's upper atmosphere at high latitudes. Charged ring particles follow these field lines. They spiral downward along the magnetic field, out of the ring plane and into the atmosphere. They enter Saturn's upper atmosphere and deposit there. This process is called ring rain. It was measured by Cassini using multiple complementary instruments. The spacecraft detected infrared emission from Saturn's upper atmosphere at specific wavelengths produced by the chemistry initiated when ring material entered the atmosphere and reacted with the ionosphere. It detected compositional changes in the ionosphere at latitudes where the relevant magnetic field lines intersect the ring plane. The measurements from different instruments were consistent with each other. Ring material is entering Saturn's atmosphere at a significant and ongoing rate. The estimated mass flow ranges from approximately 4,400 to 29,000 pounds per second. That range reflects measurement, uncertainties, and natural variability. Even at the lower bound of the estimate, even at 4,400 pounds per second, the cumulative mass transfer over geological time is enormous. At the upper end of the estimate, roughly 29,000 pounds per second, the annual loss from the rings is staggering. At rates in this range, the ring system as we know it today would be substantially depleted within a few 100 million years. The rings that Chrysalis's destruction created are draining back into Saturn through a process that involves the magnetic field, which was shaped by the helium rain, which is an interior process running on billion-year timescales. Chrysalis is being erased by the planet it fed. Titan is participating in this process indirectly. Titan is Saturn's largest moon, roughly 3,200 miles across, with a dense nitrogen atmosphere and a complete methane cycle. It orbits Saturn at an average distance of about 760,000 miles, and it is moving outward. Cassini tracked Titan's position over years with enough precision to measure its orbital drift. Titan is migrating outward at a rate of roughly 4 inches per year. Over millions of years, this migration significantly changes Titan's orbital distance from Saturn. The rate is actually faster than planetary scientists had predicted from previous models. This tells us that the tidal interaction between Saturn and Titan is more efficient than the models assumed, which in turn tells us something about the internal structure of Saturn and how efficiently it dissipates tidal energy. As Titan moves outward, it changes its gravitational resonances with the other moons. These resonances affect the orbital evolution of the entire satellite system. Some of those orbital changes are transmitted to the ring system through gravitational interactions. Titan's gradual departure is one of the long-range factors contributing to the ring system's evolution and eventual disappearance. It was also, over the history of the solar system, one of the agents that destabilized Chrysalis's orbit and set in motion the sequence of events that created the rings. Titan helped destroy the moon, whose destruction made the rings. Titan is now slowly helping to dissolve the rings that the destruction created. Then there is the Phoebe ring. In 2009, researchers using infrared data from the Spitzer Space Telescope and coordinated ground-based observations announced the discovery of a ring around Saturn that no previous instrument had detected. A ring aligned with the orbit of Saturn's outer moon, Phoebe. The Phoebe ring extends from roughly 4.8 million miles to approximately 7.8 million miles from Saturn. The main visible ring system spans less than 200,000 miles. The Phoebe ring spans millions. At its largest extent, the entire main ring system, the rings visible in every photograph of Saturn, could fit inside the Phoebe ring dozens of times over. But the Phoebe ring is completely invisible to optical telescopes. It is so tenuous, so sparsely populated, that it produces no detectable reflected light. Only its thermal emission, the heat radiated by its cold particles, gives it away in the infrared. It had been there, enormous and invisible, for as long as Phoebe has been scattering debris from its surface. And nobody knew about it until infrared technology became sensitive enough to detect it. The Phoebe ring is composed of debris blasted off Phoebe's surface by meteorite impacts. Phoebe itself is a captured body, not a moon that formed in place within the Saturnian system. It almost certainly originated in the outer solar system, possibly from the same population of icy bodies that populates the Kuiper belt beyond Neptune. It was captured by Saturn's gravity at some point in the early solar system, billions of years ago. Phoebe orbits Saturn retrograde, in the opposite direction from Saturn's rotation and from the orbits of all Saturn's regular moons. This retrograde motion is the hallmark of a captured body. Regular moons that formed from the same disk of material as the planet orbit prograde. Captured moons frequently orbit retrograde. Material ejected from Phoebe by impacts enters orbits similar to Phoebe's retrograde in the outer Saturn system. This material slowly drifts inward under the combined effects of solar radiation pressure and the Poynting-Robertson effect, which gradually drains energy from orbiting particles and causes them to spiral inward. As the inward drifting Phoebe ring material reaches the orbit of Iapetus, something interesting happens. Iapetus orbits Saturn prograde, moving forward through space. The Phoebe ring material is approaching from the retrograde direction, moving in the opposite direction. The leading hemisphere of Iapetus, the hemisphere facing forward in its orbit, sweeps up this dark, carbon-rich Phoebe ring debris head-on. The trailing hemisphere, facing away from the direction of orbital motion, doesn't encounter the Phoebe ring material. Over millions of years of accumulated impacts, the leading hemisphere of Iapetus becomes coated in a layer of dark organic debris from Phoebe. The trailing hemisphere stays bright. The result is the two-toned appearance of Iapetus, one hemisphere as reflective as fresh snow, the other as dark as coal. Cassini, the astronomer, not the spacecraft, observed this color asymmetry in the 1670s and documented that Iapetus was only detectable on one side of its orbit around Saturn because the dark hemisphere effectively disappears against the past sky. He had no explanation. For 300 years after that observation, the explanation was unknown. 300 years of documented observation of an anomalous color asymmetry on a moon of Saturn without understanding the cause. Then, we found the Phoebe ring. An enormous structure that had been there the entire time, invisible to every instrument we had used, leaving its signature written clearly on iapetus for astronomers to puzzle over since the 1670s and remaining undetected until the 21st century. The ring left its mark on a moon for 3 centuries. It waited quietly until we built instruments sensitive enough to find it. The Cassini mission was announced in 1990. The spacecraft launched on October 15, 1997. It was the product of a scientific collaboration between NASA, the European Space Agency, and the Italian Space Agency, and it represented the most ambitious and complex mission to the outer solar system that had ever been undertaken at the time of its design. 12 science instruments. A main spacecraft weighing about 6 tons, and attached to its side, the Huygens probe, built by the European Space Agency. The mission could not travel directly to Saturn. A direct trajectory would have required a launch vehicle far larger than anything available. Instead, Cassini flew on a complex gravity assist trajectory. It swung past Venus in April 1998, past Venus again in June 1999, past Earth in August 1999, past Jupiter in December 2000. Each flyby bent the spacecraft's trajectory and increased its speed without requiring onboard fuel. By the time Cassini reached Jupiter, it had been traveling for 3 years. The Jupiter flyby also provided an opportunity for science. Cassini observed Jupiter's atmosphere, its moons, and its magnetic environment during the flyby, and produced results that were published before the spacecraft even reached its primary destination. On July 1, 2004, Cassini reached Saturn. The spacecraft fired its main engine for 96 minutes to decelerate enough to be captured by Saturn's gravity. 96 minutes of continuous engine burn. If the burn had failed, or been too short, or too long, Cassini would have passed through the Saturn system on a hyperbolic trajectory and continued outward into the solar system, never to return to Saturn. The burn worked. Cassini entered orbit. It had not traveled alone. Attached to Cassini's side was the Huygens probe, named after Christian Huygens, the astronomer who had solved Galileo's Saturn puzzle in the 1650s. Huygens was designed for a single mission: descend through Titan's atmosphere, transmit everything. On Christmas Day, 2004, Cassini released Huygens. The probe coasted silently toward Titan for 3 weeks on a pure ballistic trajectory, making no corrections, following exactly the path Cassini had set for it. There was no second chance. On January 14, 2005, Huygens hit Titan's upper atmosphere at approximately 12,400 miles per hour. The heat shield glowed. Temperatures on the shield's outer surface briefly reached around 18,000 degrees Fahrenheit. The shield held. A pilot parachute deployed. The main parachute followed. Huygens decelerated from hypersonic velocity to a gentle downward drift through Titan's thick, orange-tinted haze. The descent lasted 2 hours and 27 minutes. For every second of those 2 hours and 27 minutes, Huygens transmitted. Temperature at every altitude. Pressure. Wind speed and direction, measured by tracking the Doppler shift in the probe's radio signal as winds pushed it horizontally. Chemical composition of the atmosphere at every level, measured by an onboard gas, chromatograph, and mass spectrometer. Acoustic data, sounds in the atmosphere. Electrical field measurements. And images when the haze thinned enough to allow them. The chemistry Huygens measured was remarkable in its complexity. Titan's atmosphere is roughly 95% nitrogen and a few percent methane, but trace amounts of dozens of additional compounds were detected. The solar ultraviolet light and energetic electrons from Saturn's magnetosphere continuously energize the atmospheric chemistry, breaking apart nitrogen and methane molecules and driving recombination reactions that produce complex organic compounds, nitriles, hydrocarbons, polycyclic aromatic compounds, complex polymers called tholins, which are similar in some respects to the kinds of organic material that may have existed in Earth's atmosphere before the emergence of life. Nobody is suggesting life on Titan. But the organic chemistry of Titan's atmosphere is not categorically different from pre-biological chemistry. The difference is temperature. Titan is far too cold for liquid water. The chemistry runs on liquid methane instead. The surface image that Huygens returned showed a landscape of rounded pebbles made of water ice, smoothed and shaped by the flow of liquid methane over long periods. A dry channel or flat plain, hills in the distance. An orange sky above, lit dimly by sunlight, filtered through the thick haze. It was alien. The pebbles were the wrong material. The sky was the wrong color. The atmosphere would kill you. But the geomorphology was familiar. Rounded rocks in a channel. River rocks. Carved by flowing liquid, just as river rocks on Earth are carved by flowing water. Methane rivers carve Titan's surface the same way water rivers carve Earth's. Huygens transmitted from Titan's surface for 72 minutes after landing. Then its battery ran out. 72 minutes of surface transmission from a moon more than 1 billion miles from Earth, across 1 billion miles of vacuum at the speed of light, through Cassini to a relay antenna, and then across the inner solar system to a receiving dish on the ground. In 72 minutes, Huygens gave us more direct data about another moon's surface than we had from any comparable body. Cassini continued in orbit, conducting flyby after flyby of Saturn's moons over the following decade. 127 close approaches to Titan, 23 to Enceladus. Multiple passes by Dione, Rhea, Mimas, Iapetus, Tethys. And in 2005, during an early close approach to Enceladus, it found something nobody had expected. An anomaly in Saturn's magnetic field near the tiny moon. The field was being deflected, distorted. Cassini flew closer. And it flew directly through a plume of water vapor and ice particles erupting from near Enceladus's south pole. The south polar region of Enceladus was active, warm. The tiger stripe fractures, 4 roughly parallel fissures in the ice near the south pole, each approximately 80 miles long, were venting material into space at roughly 1,000 miles per hour. The material rose hundreds of miles above the moon's surface. Material that escaped Enceladus's gravity entirely was being continuously added to Saturn's E-ring, which turned out to be not a passive ring of captured debris, but an actively replenished structure fed by Enceladus's eruptions. Cassini flew through the plume multiple times over the mission, using its mass spectrometer and other instruments to sample the composition directly. Water vapor, the dominant component, carbon dioxide, methane, molecular hydrogen, complex organic molecules, including oxygen-bearing compounds, silica nanoparticles, which form when liquid water interacts with silicate rock at elevated temperatures, dissolving minerals that later crystallize as nanometer-scale silica grains when the water cools. Sodium chloride, salt. Salt means the water inside Enceladus has been in contact with rock long enough to dissolve minerals from it. That's a liquid water ocean in contact with a rocky floor. That's an ocean with a geological substrate and molecular hydrogen. On Earth, molecular hydrogen is produced by serpentinization, the chemical reaction between liquid water and silicate rocks at elevated temperatures. Serpentinization occurs at hydrothermal vents on Earth's ocean floor, where hot water from below the crust percolates through rock and returns to the ocean, carrying dissolved minerals and molecular hydrogen. Hydrothermal vents support ecosystems entirely independent of sunlight. Chemosynthetic organisms use the chemical energy in the vent fluids as their primary energy source. Communities of organisms that have never been exposed to a photon of sunlight. Life that runs on chemistry from the deep rock. The presence of molecular hydrogen in Enceladus's plumes, combined with the silica nanoparticles and the salt, points to the same process occurring inside Enceladus. Liquid water in contact with warm silicate rock. Hydrothermal vents. At the bottom of a global subsurface ocean beneath miles of ice. Enceladus, 313 miles across, is the smallest body in the solar system, where direct observational evidence points to active hydrothermal chemistry in a liquid water environment. Cassini couldn't search for life. Its instruments weren't designed for astrobiology. Detecting microbial life in a water sample requires specialized analytical tools, the ability to identify biological molecular signatures, to distinguish biological from non-biological chemistry that Cassini simply did not carry. Nobody knew Enceladus was going to be what it turned out to be when the mission was planned. But Cassini gave us the map, the coordinates, the specific evidence. There is a subsurface ocean. It is in contact with warm rock. Hydrothermal chemistry is occurring. The products of that chemistry are venting through the ice into space, where a passing spacecraft can fly through and sample them without landing. Enceladus is advertising its interior. It is broadcasting its chemistry into space in a plume that any sufficiently equipped spacecraft can fly through and read. If life exists inside Enceladus, its biochemical products may already be present in the plume material. The question of whether life exists there is one of the most profound open questions in planetary science, and it could potentially be answered by a relatively simple mission to fly through the plumes with the right instruments. As Cassini's operational life moved toward its close, the question of how to end the mission carried weight that went beyond the purely scientific. Enceladus had been established as a potentially habitable environment with an active liquid water ocean. Titan had been established as a chemically complex world with possible relevance to pre-biological chemistry and conceivably to exotic forms of life operating in liquid methane rather than liquid water. These are not worlds you crash your spacecraft into casually. International planetary protection guidelines, developed over decades to prevent cross-contamination between worlds, require that spacecraft be disposed of in ways that eliminate any possibility of contaminating environments that might support life. Cassini was not sterile. No spacecraft sent on a years-long mission is sterile. Despite the cleaning procedures applied before launch, the biological burden reduction applied to spacecraft heading for potentially habitable environments It is not possible to guarantee that no microbial life from Earth survived somewhere on the spacecraft's exterior, in a protected location, under thermal insulation, in a joint, in a space too small for the cleaning protocols to reach. Microbial life on Earth is tenacious and inventive. If Cassini were left in an uncontrolled orbit at the end of its mission, there was a real possibility that it would eventually, over years or decades, be gravitationally perturbed into a collision with Enceladus or Titan. That collision would potentially deposit terrestrial microbial life into an environment we're trying to study for signs of indigenous life. It would permanently contaminate the data. The solution was clear, if unfortunate. Cassini would end its mission in Saturn's atmosphere. Saturn itself is not considered a priority target for astrobiology. The planet's atmosphere would destroy the spacecraft completely, incinerate it. Nothing of Cassini would survive to reach anything deeper inside Saturn. No contamination of the potentially habitable moons was possible from this outcome. Mission planners spent the final years of the mission designing what became known as the Grand Finale. 22 orbits, executed in the final months before the atmospheric entry, that would take Cassini through a region of the Saturn system it had never visited. The gap between Saturn's innermost ring and the planet's upper atmosphere, a region approximately 1,000 miles wide, a region that had never been entered by any spacecraft. Each of the 22 Grand Finale orbits was an opportunity. Gravitational field measurements at close range, precise enough to constrain models of Saturn's internal mass distribution, giving the best available constraints on core size and layered structure. Direct atmospheric sampling. Cassini's mass spectrometer was close enough to sample atoms and molecules directly from Saturn's upper atmosphere, giving chemical measurements impossible at any greater distance. Close-range imaging of the rings from below, revealing structural details invisible from the orbital perspectives the spacecraft had occupied for 13 years. Magnetic field measurements at distances close enough to the planet to constrain the detailed geometry of the field near its source. The 22 Grand Finale orbits generated a scientific return comparable to a dedicated mission on their own. The data from those passes continues to be published in scientific papers years after Cassini's operational end. On September 14, 2017, Cassini made its last close approach to Titan. Titan's gravity bent the spacecraft's path one final time. The trajectory after the Titan flyby was committed. No engine burn could correct it. Saturn's gravity was taking Cassini home. Before the final descent, with its instruments still operational and its cameras still functioning, Cassini turned to observe Enceladus. A small, bright crescent in a black sky. Saturn's most extraordinary moon, glowing. The south polar plumes were invisible at that distance and resolution, but they were there. They are always there, venting continuously, as they had been throughout Cassini's entire mission, as they presumably had been for millions of years before. Then Cassini turned its high-gain antenna toward Earth. It aligned itself precisely, and it began transmitting its final telemetry. On September 15, 2017, at 9:16 in the morning Eastern Time, the signal from Cassini was lost. The spacecraft had entered Saturn's upper atmosphere. The atmosphere was thickening with altitude descent. Cassini's attitude control thrusters fired continuously to maintain the antennas pointing at Earth. They fought the atmospheric drag. they could compensate for the initial atmospheric resistance. But as Cassini descended and the atmosphere thickened, the drag overwhelmed the thrusters. The spacecraft began to tumble. The antenna drifted away from its alignment with Earth. The signal became incoherent. Then it was gone. 83 seconds from the moment of significant atmospheric contact to the final loss of signal. During those 83 seconds, Cassini's instruments were still taking measurements. The mass spectrometer was still sampling atoms from Saturn's upper atmosphere, measuring their identities and abundances, transmitting numbers back toward Earth. Up to the last possible moment, Cassini was doing science. It incinerated about a minute and a half later. What it left behind is not the absence it might seem. Hundreds of gigabytes of scientific data, thousands of published papers, maps of Saturn's magnetic field and gravitational field, close-range images of the rings, direct atmospheric composition measurements from multiple altitudes, the discovery of Enceladus's subsurface ocean, the discovery of Titan's full methane cycle, a list of questions that will define planetary science for a generation, and a measurement made on the way in the 83 final seconds of Saturn's upper atmospheric composition at close range, data that continues to be analyzed and published. Cassini ended. The science continues. Saturn is also, structurally, a machine for producing moons. It has 83 known moons as of the last major count, which makes it the planet with the most confirmed moons in the solar system. This count has grown dramatically with improvements in telescope sensitivity. In 2023 alone, astronomers using ground-based telescopes discovered dozens of previously unknown small moons orbiting Saturn at large distances. These are not moons in the familiar sense of large round worlds like Titan or Enceladus. They are small, irregularly shaped, captured bodies, many only a few miles across, orbiting at distances of millions of miles from Saturn in highly inclined and often retrograde paths. They are survivors of the same population of outer solar system bodies that Phoebe came from. Bodies that drifted into Saturn's gravitational sphere of influence billions of years ago and were captured. Their orbital families tell the history of capture events. Several groups of small outer moons share similar orbital inclinations and compositions, suggesting that they're fragments of larger captured bodies that broke apart at some point after their capture. Collisions in the outer Saturn system have been shaping the moon population throughout the planet's history. The number of Saturn's moons is not a fixed quantity. It depends on how sensitive your telescope is and how long you're willing to watch. There may be hundreds of small moons we haven't found yet. Saturn's gravitational sphere of influence extends to enormous distances. Objects as far as several million miles from Saturn can maintain stable orbits indefinitely. The complexity of the satellite system, from tiny, captured irregular moons to Titan with its nitrogen atmosphere to Enceladus with its hydrothermal vents, reflects 4.5 billion years of accumulation, capture, collision, and disruption. The Moon system is not a stable, static configuration. It's an ongoing dynamical process. Moons influence each other. They influence the rings. They influence the larger moons through resonances. The whole system is in slow, continuous motion. Chrysalis was part of that system. Titan is part of that system, drifting outward. The ring system is part of that system, replenished by Enceladus in the E-ring and draining back into Saturn through ring rain. Every component is connected to every other through gravity and time. The question of why Saturn has a hexagon and Jupiter doesn't is one that planetary scientists have been investigating since the discovery. Jupiter's north and south poles have no hexagonal structure. Jupiter's poles show large, organized cyclonic storms, multiple oval vortices at high latitudes, and complex jet stream patterns, but not hexagons. Why Saturn and not Jupiter? Jupiter is larger. Jupiter rotates faster, with a day of about 9 hours 50 minutes, compared to Saturn's approximately 10 hours 33 minutes. Jupiter has more internal heat. Jupiter has a different wind structure. The laboratory experiments that produce hexagons in rotating fluid tanks suggest that the number of polygon sides, whether you get 4 sides, 5, 6, or more, depends on the ratio between the rotation speed of the inner cylinder and the outer container. In a planetary context, this translates to the relationship between the rotation rate of the deep interior and the rotation rate of the atmospheric layer near the pole. Saturn's atmospheric wind speeds at high latitudes, the jets that bound the hexagonal structure, may place the system in exactly the parameter regime that produces a 6-sided rather than a 4-sided or 8-sided structure. Jupiter's parameters may fall outside the range that produces stable polygon waves, or may produce a polygon that is suppressed by Jupiter's more vigorous internal convection. This is a plausible explanation. It's not a proven one. The full quantitative model that predicts the hexagon's stability and persistence from first principles, using Saturn's actual atmospheric parameters rather than laboratory analogues, doesn't exist yet. The laboratory experiments demonstrate the physics. They don't close the question of why Saturn's hexagon is as stable as it is, or why it has exactly 6 sides and not 5 or 7, or why it persists through polar night when solar driving is absent. The Webb data from November 2024, showing the hexagon as a deep thermal structure spanning multiple altitudes, adds a new constraint. Any valid model of the hexagon must now explain not just its shape at one altitude, but its coherent, 3-dimensional structure. A model that accounts for a surface hexagon doesn't automatically account for a hexagon that reaches into the stratosphere. The constraint tightened. The modeling challenge deepened. There's another Saturn anomaly that deserves mention alongside the magnetic field and the hexagon: the planet's internal structure. Specifically, the question of what's at the center. Saturn is generally modeled as having a dense core surrounded by layers of metallic hydrogen, then molecular hydrogen, with helium mixed throughout and concentrated more heavily at depth from the rain process. The core is expected to be a mixture of rock, metal, and ice, compressed to extreme density. But the exact size and composition of the core are uncertain. Cassini's grand finale, measurements of Saturn's gravitational field, provided the best constraints on the internal mass distribution. And the picture that emerged was more complicated than the simple layered model. The gravitational field measurements are consistent with a core that is not sharp and compact, but diffuse. A fuzzy core. Instead of a clear boundary between the core and the overlying metallic hydrogen, the models suggest a gradual transition, a zone where the heavy core material, the rock and ice, is mixed with overlying metallic hydrogen over a large radial distance. This fuzzy core model is consistent with the idea that a giant impact early in Saturn's history could have disrupted and mixed the original compact core with the surrounding material. or it may reflect gradual erosion of the core boundary by convection from above over billions of years. Or it may be a consequence of the conditions under which Saturn formed. The same ring seismology that has been used to probe Saturn's rotation rate has also been used to look for oscillation modes that probe the internal structure. Normal mode oscillations, analogous to the way earthquakes propagate seismic waves through Earth's interior, propagate through Saturn's interior and produce density waves in the rings at specific resonant locations. By identifying these ring features and matching them to specific oscillation modes, researchers can infer properties of the interior. This technique has confirmed the existence of stable stratification in Saturn's interior at intermediate depths, consistent with the helium differentiation picture. It has also indicated that Saturn's core region may have a complex, mixed composition rather than the simple compact core of earlier models. Saturn's interior is still being mapped from the outside, through the rings, from the seismic waves the planet itself is producing. Its planetary seismology conducted without a seismometer on the surface, using the rings as a passive detector. The technique is elegant. The answers it's returning are complicated. The James Webb Space Telescope, the instrument that returned the November 2024 Saturn data, is worth understanding in the context of what it can do that no prior observatory could. Webb operates in the infrared. Its primary mirror is roughly 21 feet across, more than 2.5 times the diameter of Hubble's mirror. It orbits at the second Lagrange point, about 1 million miles from Earth, on the side away from the Sun, where it can maintain a stable cold temperature necessary for infrared sensitivity. To detect infrared emission, the telescope itself must be kept extremely cold, otherwise its own thermal emission would overwhelm the faint signals from distant objects. Webb's operating temperature for its coldest instruments, including MIRI, is about -447 degrees Fahrenheit, just 12 degrees above absolute zero. At that temperature, MIRI's detectors can detect infrared emission from objects that would be invisible in the wavelength ranges that Hubble or Cassini's imaging cameras were designed to observe. Saturn, at visible wavelengths, shows its reflected sunlight, cloud patterns, atmospheric banding, the hexagon in cloud structure. Saturn, in MIRI's infrared wavelength range, shows the planet's own thermal emission, not reflected light, heat. The thermal structure of the atmosphere at different altitudes, which corresponds to different temperatures. The hexagon, visible in cloud structure at one altitude in visible light, showed up in Webb's infrared data as a thermal feature coherent across multiple altitude levels simultaneously. This is precisely the kind of information that prior instruments could not provide. Cassini had infrared instruments, but they operated at shorter wavelengths and with lower spatial resolution than Webb's MIRI. Ground-based infrared observatories can observe Saturn at some infrared wavelengths, but Earth's atmosphere absorbs many of the most diagnostic wavelengths. Webb's wavelength coverage, its sensitivity, and its position above Earth's atmosphere give it access to a view of Saturn that was simply not available to any prior observatory. The November 29, 2024 observation was not a routine monitoring observation. It was a targeted campaign specifically designed to probe Saturn's polar region in detail at Webb's wavelengths. The result exceeded expectations. The dark, drifting features within the polar structure were not predicted. The multi-altitude thermal coherence of the hexagon was clearer than previous data had established. The auroral detail was richer than anticipated. Webb will observe Saturn again and again. Each observation adds to a dataset that is slowly building a picture of how Saturn's polar dynamics evolve over time, how the hexagon changes between observations, if at all, how the auroral activity correlates with solar wind conditions, and with the internal variability in the radio emissions. Long-term monitoring of Saturn with Webb is one of the ongoing programs in the telescope's schedule. The November 2024 data is a beginning, not an end. The broader context for what Saturn represents in planetary science deserves a moment. Saturn is not just an interesting planet in itself. It is a template for understanding gas giants generally. Exoplanet surveys have discovered thousands of gas giants orbiting other stars. Many of them orbit close to their host stars, closer than Mercury orbits our Sun. Others orbit at Saturn-like distances. We cannot directly image their interiors. We cannot send spacecraft to orbit them. What we can do is observe their masses, their radii, their atmospheres in limited ways through transit spectroscopy and their orbital dynamics. To interpret what those limited observations are telling us about the physics of those planets, we need calibration objects. Planets where we have detailed, close-range information to build and test models. Jupiter and Saturn are our two best calibration objects for gas giant science. Everything we learn about how metallic hydrogen behaves inside Saturn, about how helium differentiates, about how the magnetic dynamo operates in a planet of Saturn's mass and composition, directly improves our ability to interpret observations of exo-gas giants. When astronomers measure the radius of a Saturn-mass planet orbiting another star and find that it's inflated, larger than models predict, they're asking whether there might be an additional heat source operating inside it, the way helium rain operates inside Saturn. When they observe magnetic field signatures in the radio emission from distant giant planets, they're applying the lessons of Saturn anomalous myriometric radiation. When they try to determine the rotation period of an exogas giant from its radio emissions, they're aware of the caution that Saturn has taught them. The radio period may not reflect the interior rotation. Saturn is not just a planet to study for its own sake. It is the field site where we develop the tools and concepts we need to understand planets we can never visit. Every anomaly Saturn presents, every unexpected result from Webb or Cassini, is a test of models that will eventually be applied to planetary systems we can only observe from light years away. Getting Saturn right is not just about Saturn. It's about understanding the class of objects that Saturn belongs to, a class that includes billions of planets across the galaxy. Saturn also sits at the center of a long-standing question about the timing of the solar system's formation. The Grand Tack hypothesis, one of the leading models of how the solar system achieved its current architecture, proposes that Jupiter and Saturn formed in the outer solar system, then migrated inward together, disrupting the early inner solar system, before migrating back outward to their current positions. This inward and outward migration of the two gas giants would have scattered asteroids and comets inward toward Earth, potentially delivering water to our planet and shaping the size distribution of the terrestrial planets. In this model, Saturn plays a foundational role in Earth's habitability. Without Saturn's gravitational influence, stabilizing Jupiter's migration and reversing it before Jupiter consumed too much of the inner solar system, Earth might not exist in anything like its current form, or might not exist at all. Saturn's role in the solar system's architecture is not passive. The planet's gravity shapes the trajectory of asteroids and comets. It has deflected many potential impactors away from the inner solar system over billions of years. it has also sent some inward. The debate about whether Jupiter and Saturn act as net protectors or net threats to Earth from asteroid impact is not fully resolved. The answer appears to be both, depending on the object and the configuration. What is not disputed is that Saturn's gravity is a major shaping influence on the dynamics of the entire solar system. Remove Saturn, and the orbital architecture of the solar system changes fundamentally. The asteroid belt would behave differently. Cometary fluxes into the inner solar system would be different. The long-term stability of Earth's orbit, which depends partly on the gravitational influence of the outer planets, would be different. Saturn is not just one of several roughly equivalent planets. It is one of the two massive gravitational anchors of the outer solar system, and its presence is woven into the conditions that made our planet what it is. That context does not appear in most discussions of Saturn's anomalies. It should. The anomalies we've discussed, the unexplained rotation rate, the hexagon, the helium rain, the young rings, are features of a planet that has been exercising gravitational influence on the entire solar system since its formation. Every one of those anomalies is a window into the interior of an object that has been shaping the environment in which Earth evolved. That gives the anomalies a weight beyond pure planetary science. Saturn's atmosphere also has a structure worth understanding in more detail, because it's the context in which both the hexagon and the megastorms operate. The visible banding of Saturn's atmosphere, the alternating lighter and darker bands you can see in photographs, reflects an underlying pattern of alternating east-flowing and west-flowing jet streams. These jets extend deep into the atmosphere. Precisely how deep is a matter of ongoing research. Cassini's gravity measurements during the grand finale suggested that the jets extend to depths of several thousand miles below the visible cloud tops, much deeper than similar jets on Earth, which are confined to the thin troposphere. Deep jets are a consequence of Saturn's large size and rapid rotation, combined with its predominantly hydrogen composition. The very deep jet structure implies that when the megastorm breaks out, it is not just a shallow atmospheric event. The convective plume that initiates the storm reaches upward from the water cloud level, which lies deep in the atmosphere, where pressure is many times Earth's surface pressure. It taps energy stored across a large, vertical column. The storm's influence extends from the deep troposphere into the stratosphere. The chemical traces that Cassini detected in Saturn's stratosphere years after the 2010 storm had been carried up from depth by the storm's initial convective eruption. The stratosphere of Saturn, normally isolated from the troposphere by a stable layer, was breached by the convective violence of the storm. Material from deep in the atmosphere ended up in the stratosphere. That material included exotic chemistry that photochemical models of the stratosphere had not predicted. Saturn's stratosphere was changed by the storm. The change was temporary, lasting years rather than decades. But it happened. The storm didn't just affect the weather layer. It reached up into the stratosphere and changed its composition for years afterward. Saturn's atmosphere is not a series of neatly separated layers that operate independently. The storm showed that the layers are coupled. Energy and material can be transported from deep in the atmosphere to high altitudes by a large enough convective event. The hexagon, existing at the boundary between the troposphere and the stratosphere, and possibly extending into the stratosphere, as Webb's MIRI data suggests, may represent a different kind of coupling. A dynamical coupling that persists continuously rather than erupting catastrophically every 30 years. two different expressions of the same underlying planetary property, the connection between deep interior and upper atmosphere, one continuous and geometric, one periodic and violent, both traceable to the interior heat. The specific orbital mechanics of Saturn within our solar system also produce observational opportunities and constraints that are worth noting. Saturn's orbital inclination relative to the ecliptic is only about 2.5 degrees, meaning it orbits close to the plane shared by most of the other planets. Its orbital period is approximately 29.5 Earth years, meaning that from Earth, Saturn completes one lap of the zodiac in about 3 decades. The ring tilt changes relative to our line of sight as Saturn orbits. Every 15 years or so, the rings appear edge-on from Earth, becoming nearly invisible. In between, the rings open up to increasingly favorable viewing angles. The most recent ring plane, crossing from Earth's perspective, occurred in 2025, offering observers a rare configuration in which the rings appeared edge-on, and the planet's disk was visible without the rings dominating the view. Webb observations during that window allowed study of Saturn's atmosphere in a geometry that hadn't been available for years. Ground-based amateur astronomers have been observing Saturn for generations. The rings' changing tilt, the appearances and disappearances of the Cassini division, the occasional transit of Titan or Enceladus across the disk, the periodic great storm events. All of these are phenomena that can be followed from a backyard telescope under favorable conditions. Saturn is one of the few objects in planetary science where dedicated amateur observers with modest equipment can contribute genuine observational data. Reports from amateur observers have historically contributed to the documentation of Saturn's storm events. The 2010 Great White Spot was first reported by an amateur astronomer. That's not a footnote. That's a professional quality detection made by someone with a telescope in their backyard. Saturn rewards attention. It rewards long-term monitoring. It rewards the kind of patient, ongoing observation that has characterized astronomy at its best, since Galileo first squinted through a primitive telescope and couldn't figure out what he was seeing. 400 years of looking, still surprising us. Here is the complete picture. Saturn is a planet shaped from the inside out by a process that began when the solar system was young. Helium rain has been falling through its metallic hydrogen interior for over 4 billion years, releasing gravitational energy as heat, depleting the upper atmosphere of helium, and modifying the conditions in which the magnetic dynamo operates. That rain is still falling now. Right now. As you read this, the helium rain generates excess heat that fills the thermal accounting gap that Kelvin-Helmholtz contraction cannot fill. That heat drives atmospheric convection on timescales ranging from decades, the Great White Spot cycle, to geological ages, the ring system's long-term evolution. The heat shapes the dynamo. The helium differentiation has created a stratified intermediate layer between the metallic hydrogen zone and the outer molecular hydrogen envelope, and that layer filters the magnetic field, suppressing its asymmetric components before they reach the surface. The result is the near-perfect magnetic alignment that standard dynamo theory cannot explain, the alignment that Webb observed in its auroral imaging and that the radio emission data hints at through the different northern and southern emission periods. The magnetic field, filtered and nearly symmetric, interacts with the ring system. Ring waves, driven by resonances with the moons, propagate through the rings, drive atmospheric oscillations, and those oscillations modulate the radio emissions. The modulation is what confused us into thinking we knew the rotation period. We still don't. At the North Pole, a hexagonal wave structure has persisted through over 45 years of direct observation. It ran unchanged through the entire duration of polar night. It reached through multiple atmospheric layers simultaneously, as Webb's MIRI data showed in November 2024. It hosts dark, drifting features in the infrared that no model predicted and that are still being characterized. It is maintained by internal dynamics, and whatever those dynamics are, they are robust against everything an outer solar system atmosphere throws at them. The rings are young, between 10 million and 100 million years old. They came from Chrysalis, a moon disrupted inside Saturn's Roche limit, whose destruction also set Saturn's axial tilt. The tilt explains the polar seasons, the hexagon's polar night survival, the 30-year storm cycle. Everything is connected. The rings are draining into Saturn at thousands of pounds per second via ring rain, a process driven by the magnetic field, which is shaped by the helium rain. The moon that made the rings is being reclaimed by the planet that made the rain. Titan is slowly migrating outward at 4 inches per year. The Phoebe ring, enormous and invisible, coated Iapetus and left a 3-century-old observation with no explanation until infrared instruments found the source in 2009. Enceladus is erupting from a subsurface ocean with molecular hydrogen, silica nanoparticles, salt, and organic chemistry pointing directly at hydrothermal activity in a liquid water environment. And Cassini, the mission that measured most of this, burned up in Saturn's atmosphere in September 2017, transmitting until the signal failed, pointing its antenna at Earth in its final seconds. This is not a collection of separate anomalies. This is one planet, one system, connected from core to ring to radio signal. Driven by 4 billion years of helium rain and expressing itself at every level, we have the instruments to measure. When you look at Saturn in a photograph or through a telescope on a clear night when it's well placed in the sky, the appearance is unmistakable. Serene, ringed, still, the rings catching the light. The planet itself glowing a soft, pale gold. The shadows of the rings falling across the disk. That image is accurate in a literal and narrow sense. From 886 million miles, Saturn does look serene. But underneath that appearance is a radio signal 2 hemispheres generate at different frequencies. A signal whose origin, after 40+ years of study, is still not definitively explained. A hexagonal wave structure at the North Pole that has run unchanged through polar night and full seasons, maintained by processes feeding it from below. A rain of liquid helium falling through metallic hydrogen right now, converting gravitational energy to heat, depleting the upper atmosphere, generating the excess luminosity, shaping the magnetic field, and sustaining the anomalies we're still trying to explain. Rings young enough that they didn't exist when our earliest human ancestors were walking the Earth, draining back into the planet at a measured and ongoing rate. Megastorms that build for 30 years on stored interior heat and then erupt with lightning energetics equivalent to a year of Earth's solar input. A moon with a liquid water ocean, warm rock at the seafloor, and hydrothermal chemistry broadcasting itself into space through active eruptions. And the spacecraft that found all of this, pointing its antenna home for 83 seconds before the atmosphere took it. Saturn is not the serene planet. It has never been. The beauty you see in photographs is the surface of something considerably more complicated. What lies below that surface? What Webb's MIRI data made sharper without resolving? What Cassini spent 13 years mapping without completing? Is a set of connected anomalies that collectively describe a planetary system still being understood after centuries of observation. That is what makes Saturn the most interesting planet in our solar system. Not its size, not its rings. The fact that 400 years after Galileo couldn't figure out what he was looking at through his primitive telescope, with a space telescope of unprecedented power now in orbit, delivering infrared data of Saturn's polar atmosphere, Saturn is still sending us things we didn't expect. Still managing to surprise us. Still running processes we cannot fully model. The universe is under no obligation to be simple. Saturn has been demonstrating that for as long as we've been looking. Good night.